And now we'll look at one example of a distributed charge, which of course means integration. We're going to look at the potential a distance d away from a line of charge that is a length L. Now we know that for point charges, you would simply take the sum, in other words, add up the potential due to each point charge. Now we know also that for integration, the sum of the point charges becomes an integral of different tiny elements of length along the line, where each tiny element of length each has a little bit of charge, so we can treat it as a point charge. So we need to find the potential due to a line of charge. So we're interested in potential at a point P that is going to be a distance d away from one end of this line of charge. Now the line of charge we'll say is L in length, and it will have a charge density lambda coulombs per meter. Now we know that the potential for a point charge at a distance r away from it is just q over 4 pi E naught r. We also know that if we had several point charges, the total potential would just be the sum of the potentials due to each charge. Here we don't have a bunch of individual point charges, but we have a continuous charge. So now we're going to be saying that V is the integral of every little element dV along the line. So let's divide up the line into little lengths dx, and each one will have a charge dq, a little bit of charge. So dq in fact will equal the charge density times the length, in other words lambda times dx. So each little length will be a distance x away from one end, and it will be the length dx with a charge dq. And we are interested in adding up the potential due to each little bit of charge. Now the distance each one will be away we will call r, and r here will just be, from Pythagoras, the square root of d squared plus x squared. So each little element dx that has its charge dq will provide a little bit of potential dV. That will be 1 over 4 pi E naught dq over r. And that will be 1 over 4 pi E naught dx times lambda, as we worked out above, over x squared plus d squared. So V is going to be the integral from naught to L, 1 over 4 pi E naught lambda times dx over x squared plus d squared. So going on from that last line, we've seen this kind of integral before, and what we find is that, keeping the constants out the front, this integral becomes a log function, log of x plus x squared plus d squared to the half. And we evaluate it at L minus 0. So we now have lambda over 4 pi E naught log of L plus L squared plus D squared to the half minus log of D. And we know that if we subtract two logs, so log of A minus log of B, it's simply log of A over B. So our final expression for V is that it is lambda over 4 pi E naught log of L plus, turn it back to a square root sign, or we could leave it as to the half over D.